So, hello everyone, let's get started. And today we are gonna continue discussing about entity relationship diagrams. After that, we're gonna start discussing about schema normalization. The last time at the end of the lecture, we have started discussing about how we can translate those entity relationship diagrams into an actual relation schema, because that is the final goal of entity relationship diagrams. They describe at a high level of abstraction what a database structure should look like. And in the end, we want to create a database schema based on those entity relationship diagrams. So the last time we have already seen how we can translate some of the basic components of those entity relationship diagrams into a relation schemata. We have seen how we can represent entities to essentially become one relation with the attributes of the entity as columns of the corresponding relation. We have seen how we can translate relationships into a schema. So for instance, we can introduce a new relation which captures the content of the relationship, which were those diamonds in the entity relationship diagram. We have also seen that we can optimize that mapping for specific types of relationships. We have classified binary relationships in particular based on how many entities can be in a relationship with other entities. And based on that classification, we have seen a couple of alternatives about how we can translate those diagrams into schemata. And those different representations, they differ by how many relations I need to introduce. In the simplest case, I can represent all of this, the two entities and the relationship between them by one single relation. All right. Now, in the following, we're gonna discuss about how we can translate some of the other features of entity relationship diagrams, starting with subclasses. As a little reminder, subclasses essentially means that one entity type is a specialization of another entity type. So it may add additional attributes, it may have specific relationships, and it adds all of these on top of the attributes and relationships of the parent class. So in order to translate those subclasses and superclasses into a relation schema, there is multiple ways. For instance, I could just store entities of the subclass and entities of the superclass in separate relations. Also, I could introduce multiple relations for each of the specific attributes. Some of those attributes are specific to the subclass. Other attributes, they also appear in the parent class. So I could introduce separate tables for those attributes, and then I would insert rows only for entities of the class to which the attribute belongs to. Another possibility would be that I just say introduce one single relation in order to store entities of the superclass and of the subclass. And if I'm dealing with entities of the superclass, they will not have all attributes for which the relation has columns, but that is maybe not such a bad thing. I can just set those corresponding entries to SQL null values in the end. Now, we will see an example on this in a minute. I believe there's a question. Okay, all right, great. So we're gonna see an example, I think, that will clarify things, but otherwise, please let me know, then we can discuss about that more. All right, so here we have one entity relationship diagram with a subclassing relationship. We have managers, which are a subclass of employees in general. And the managers, they additionally have a budget that they can spend for their projects. So that is one additional attribute that is specific to the manager class. So we can represent this by introducing two separate relations. As you see here, we can introduce the employee relation, which stores the employee ID and the job title, and the manager relation, which stores employee ID, job title, and also the budget. So here you see the manager entity does not explicitly represent the emp ID and job title attributes, but they are implicitly included because we have the subclassing relationship represented by this yellow triangle with the is a label. So that here is a first possibility. We just store different entities in different tables based on their class. Another possibility is what you see here. So there is the job title attribute, which is common to all of those entities. And then there is the budget attribute, which is specific to entities of type manager. So what we could do is that we introduce one table to include all of the common attributes. Here that is the job title, and of course we always need to include the employee ID. And then we could introduce a second relation which only stores the manager-specific attributes, which in this case is the budget. So that would be an alternative way to represent this subclassing relationship. And now for the last possibility, that is that we essentially only introduce one single table to store entities of both types. Now, the only challenge here is that if we are dealing with employee entities which are not manager entities, then we will not have any value for the budget. But what we can do in this case in our database is that we simply set the corresponding fields to SQL null. This represents that we don't have the corresponding value. All right. So I think it makes one table per class. So that I believe refers to the first possibility here. Okay, I see that was the answer to the other question. Okay, all right. So yes, so those are three different possibilities, either introducing one table per class or introducing tables for specific attributes which link the entity key, in this case employee ID, to the corresponding value for the attribute, or just one big table in which we collect everything. Then we will have a couple of holes, so to speak, in that table, which means fields that we set to null because those attributes do not belong to an entity of the corresponding class. So those are a couple of ways in which we can translate entity relationship diagrams with subclassing relationships into a relational schema. Is there any questions on this? All right. Then let's discuss a little bit about how we can translate weak entities. And as a reminder, weak entity is generally an entity which cannot stand for itself, but it belongs to another entity. An example that we have seen was, for instance, assuming that you have entities of type homework that have a homework number, but as long as you don't consider the course that those homeworks belong to, the homework number is not a unique key. So for a weak entity, it means that in order to obtain a unique key, we have to combine the partial key of the weak entity with the key of the owning entity, which in the homework example would be the course. So the way in which we represent weak entities in our relation schemata is that we introduce a new relation for storing those weak entities. And they have essentially a column that represents a foreign key reference to the key of the owning entity. If you implement that in SQL, then you also want to set specific constraints on those weak entity tables. In particular, if the owning entity should ever be deleted, then you also want to delete all associated weak entities. So if for some reason in your university database, you have homeworks and courses, and you delete the corresponding course, then all the associated homeworks should also be deleted because their foreign key references now point into the void. All right, here there's a little bit more detailed example. It is exactly the one that I mentioned. We have homeworks which belong to courses. The homework itself has a homework number, but that is not a complete key. It becomes a complete key if you combine the homework number with the course ID. And here on the bottom of the slide, let me quickly rearrange something. On the bottom of the slide, you see the corresponding relation. It has a homework number and course ID, and both together form the primary key of that relation. We also have a grade mean for that homework. And if you want to represent that as SQL commands, then this is how you can do it. Here we are creating the table homeworks with the corresponding columns. We identify the homework number and the course ID as the primary key. And we specify that the course ID refers to another table storing the courses. And we have this little addition on delete cascade, which means that if somebody deletes the course that the homework belongs to, then implicitly the homework should also be deleted. Because otherwise, without the owning entity, those big entities cannot really stand by themselves. So we should remove them in case the owner entity gets deleted. All right. So this is how we can translate some of the features of entity relationship diagrams into relation schemata for which we can find corresponding SQL commands for creating those tables. In practice, you might not always do this by hand. I mean, if you work on a serious project, then you use tools for those translations and also for drawing the entity relationship diagrams. So if you want to have a list of corresponding tools for Postgres, here you have a web address where you can find a relatively large list of tools. And the number of available tools already tells you that this is something which is done very frequently when it comes to databases. Some of those tools automatically translate your entity relationship into SQL statements. So if this is something that you want to do, I recommend you to pay attention to that, to ideally get a tool which does the translation automatically. But now you know a little bit what is going on in the background. One little caveat, the representation used for entity relationship diagrams, it differs a little bit across different books, across different courses. So be careful and make sure that you understand well what the semantics is of the elements. The representation might slightly differ from the one that we have seen here, while the concepts will most likely be the same. So those are tools that you can check out for Postgres, but there's also tools for other database systems, of course. Here, perhaps finally, one simplified entity relationship diagram of a popular database which stores information on music. And as you see here, so those are already significantly more complex than what we have seen in our examples. Also, the representation is a tiny little bit different. But the concepts are still similar. So this is just for showing you a little bit how that can look like in practice. And let me tell you that this is still a very simple database on the global scale of databases. So for other databases, it would be essentially impossible to parse the entire entity relationship diagram by one person. All right. So next, we will switch to talking about how we can optimize database schemata. So we will go away a little bit from entity relationship diagrams. Before doing that, I wanted to verify whether there's any questions on entity relationship diagrams. We're gonna switch the slides. Somebody has a question, please feel free to ask it. All right. So we're gonna continue talking about a database schema design. Now we are gonna talk about how we can optimize an initial draft of a database schema. We have seen this entire database design process where we discuss mostly about those 2 points in the middle, the conceptual design, which is drawing entity relationship diagrams, and the schema normalization, which we are about to discuss in more detail. So the goal of schema normalization is always to bring your initial schema into a more optimized form. And in the following, we are going to discuss in detail what we mean by optimized form. So this is what we are going to talk about, schema normalization, just the process of bringing it into an optimized form. The corresponding chapter in the Ramakrishnan and Garke book, that is chapter 15. All right, so with entity relationship diagrams, you model what information you want to store in your database based on some use case analysis with whatever company or entity in general you are doing the database for. And then in the next step, you want to optimize the initial draft of the database schema. Typically, the first draft of the schema introduces a lot of data redundancy. And as we will see in more detail in the following, this data redundancy can lead to various problems. So the goal of schema normalization is to get rid of that redundancy up to a certain extent. So in the following, we're going to discuss about normalization. We will not finish that in this lecture, but this will extend to the next lecture. This is the high-level roadmap of what we will discuss about. In the first step, we will talk about functional dependencies. And functional dependencies are important because they are a way to indicate a redundancy in your data. And that is what we want to get rid of in normalization. So functional dependencies are important for that reason. Then we will discuss about normal forms. And a normal schema is in a normal form if it has certain desirable formal properties with regards to data redundancy. So we will see a couple of different types of normal forms which come with different trade-offs in terms of how much redundancy they still allow and which other properties they have. And finally, we will see principled algorithms that allow you to bring any initial database schema into one of those normal forms. So that is the high-level roadmap. We start by discussing about functional dependencies. Now, as already discussed, a functional dependency allows you to detect redundancies, which is what you typically want to remove during normalization. A functional dependency always applies to one specific table, and it essentially states that the values in some columns uniquely decide the values in other columns. So if you use this notation over here, x, right arrow, y, it means that the values in x, where x is just a set of table columns, they decide the values in y, which is also a set of table columns. To be precise, I should probably say that functional dependencies, they can apply across different tables in principle, but for the purpose of normalization, we will care most about the functional dependencies that apply to one single table, meaning that x and y, those are sets of columns that are taken from the same table. All right. Let's make a little example here. So let's say we have again this university scenario, and we have a list of a table with TAs, and for each TA we have the name, the hours worked, simply distinguishing full-time and part-time, and the salary per, let's say, per week. So those numbers are not realistic, but let's use it as an example. So here we have one functional dependency at the bottom of the screen. It states essentially that the hours, the value in the hours column should imply the value in the salary column, which somewhat makes sense because when people work the same amount of time in the same job, then they should get the same salary. All right, so that at the bottom is a functional dependency where the two column sets that are referenced, they only contain one single column. In general, it could be multiple columns on both sides. Now, here we store information in the table, and we have a functional dependency which connects the hours column to the salary column. Can anyone tell me why that might be a problem? Representing the data in this way. Having this functional dependency which links the two columns in the same table. If you think about when you're working with the data. Okay, there's some proposition. Yes, very good. Okay, very good. So here, the first suggestion is if we store things in this way, then we are wasting space, because here the number of hours already implies the salary. So as long as I know which salary correlates with what hours, I don't need to store the salary in each of those rows. Yeah, wasting space, that is a great point. Okay, very good. And here there's another proposition. What happens if we suddenly decide to be generous and change the salary of the TAs and give them 5% more, for instance? I mean, in this case, I would have to go through the entire table and change it everywhere, right? Yes, yes, also. I mean, if we update the hours that a TA works, for instance, somebody who initially only wanted to work part-time and then decides to work full-time. So here we would not only have to change the hours, but also the associated salary. Yes, so those are very good points. All of this is correct. So we covered most of the problems that I see in the scenario. Right. All right, and here that is a list of the problems that we could have, plus a space consumption. That's not even mentioned here. But the three anomalies that we typically associate with the scenario, that is update anomalies, insertion anomalies, and deletion anomalies. And as you know from concurrency control, those anomalies are typically a bad thing. And here we have details what could happen. So here, for instance, if we update a data, then if I only update the payment, for instance, for one TA, I could violate those integrity constraints. I could like get inconsistent data according to this functional dependency. Moment. Also, when inserting a new TA into the database, for instance, let's assume that all my TAs so far, they work part-time, and now I have a first TA who wants to work full-time. In that case, I would need some external knowledge source in order to know which hours to insert, which salary to associate with this TA based on the hours. Because in this table, I can only store salary for TAs that I currently have working. On the other side, it might be good to store somewhere outside the link between the number of hours and the salary. If I only have this single table, I cannot store any information about salary for job hours if I don't have a corresponding TA currently stored in the database. And related to that, there's the deletion anomaly. I mean, let's say I currently have TAs, some of them are working part-time, some of them are working full-time. And for those TAs, I therefore store the number of hours worked and the associated salary. And now I delete all the TAs which are working part-time, for instance. In that case, the information, which salary I was paying for part-time work would get lost. So I want to delete the information about TAs, but I don't want to delete information about the link between the hours and the salary. So those are a couple of problems that are linked to redundancy. The solution to that is the following. I simply put this information in two separate tables. Now here I have one table specifically for associating the number of hours worked with a salary, and I have a different table associating TAs with the number of hours worked. And as you can see here, this representation is better for multiple reasons. First of all, we have less space consumption. Second, if I now delete all the TAs which are working full-time, for instance, then it doesn't mean that I'm losing information which salary is associated with full-time work, because I still have it in the other table. And also if I insert a new TA which works here I have a part-time and full-time. If I only had full-time TAs and now I would insert a part-time TA, then I could look into the other table in order to get the salary which is associated with that number of hours worked. And of course, also, if I want to change the salary of the TAs working full-time, for instance, I can just change it once in this table on the right-hand side of the screen, and then I avoid any data inconsistencies, because all the other TAs will automatically be associated with the higher salary. So this is how we resolve the redundancy. We decompose a table into different tables. All those normal forms that we see in the following, in the end, they come down to trying to be smart about how we decompose your initial tables in a way to reduce redundancy. This is the analysis of the example. We have already mentioned most of those things. The anomalies cannot really happen anymore. And here, what happened is that we still have the function dependency, but it doesn't connect columns in the same table anymore, but now it connects columns in different tables. So it becomes essentially harmless. One important point to keep in mind when decomposing tables is that you want, of course, to avoid data loss. What you need to be able to do is that if you essentially join those tables again, you need to be able to obtain the original table before the decomposition. Now here in this case, we have that because the function dependency states that the number of hours worked uniquely implies the salary. And then going back to the example here, that means that if we would join those two tables together via a natural join, meaning that we want the same values in columns that have the same name, which in this case is only the hours column. So if we join them together this way, then since the hours implies the salary, it means that for each row in the table on the left-hand side, I will find one single row in the table of the right-hand side that matches, that satisfies the join condition. So this is what we call a lossless decomposition, which is good because it means we're not losing any data. We can recompose the table in order to get the original data. But for storage, we decompose the two, which has all the advantages that we have discussed. All right. One little drawback about decomposition, we will also talk a little bit more about that later, is that in order to verify integrity constraints, or for some other operations, you might require more joins. So there's a little bit of a trade-off here. Joins are an expensive operation. We have seen all the different algorithms that people have proposed for them because they are typically the most expensive operation in practice. And if you decompose things further, it means you will potentially need additional joins at runtime. But nevertheless, the advantages are huge. This is why people often go for those normal forms. All right. Now, Let's discuss a little bit more about a functional dependency. So now we have seen how we can do this in one specific example. In the following, we're going to see a more generic process to do that. All right. So in general, functional dependency always states that the values in some column set X imply the value in some column set Y. As we have discussed, we have a redundancy if we have those functional dependencies that apply to the columns in one table. And here we store things multiple times that we essentially only would have to store once. So that is the thinking. This is why we have separated out the content, the columns that belong to the functional dependency in the previous example. During normalization, we typically want to avoid functional dependencies that apply to columns on the same table, and we achieve that by decomposition. So in general, for most of the normal forms that we see, we will try to avoid having functional dependencies that apply to columns in the same table. There's already at least one exception to that. Can anyone guess in which case it is acceptable to have functional dependencies that only link columns in the same table? In which case does it not indicate redundancy? In principle, there's multiple cases, but let's see if someone has a proposition. Okay, and this is actually, okay, that's a great remark. So, okay, very good points here, very good points here. Let me address already those. Okay, so here, one proposition is that if our functional dependency, for instance, links hours to a salary, and let's say, for instance, I currently only store one TA in my database for full-time and one TA for part-time. Then we could say at this point in time, we don't really have redundancy in our table because values are only stored once. So that is a great point. In fact, the functional dependencies may not always be associated with a redundancy. Now, the thing is that when designing the database schema, I typically don't actually know the content yet. So I try to design the database schema in a way such that I can guarantee that redundancy is avoided independently of which data I'm inserting in the future. So even if at some point in time the database would actually not contain redundancy, if I leave those columns that belong to a functional dependency together, I could have redundancy sometime in the future once people start inserting data. So that's one important point. We are going to discuss more about this. I fully agree that we might not always have a redundancy with functional dependencies, but when designing the schema, it's really about making sure that no redundancy can happen at some point in the future. So it abstracts away from the current database state. Nevertheless, I agree with that point. So there would be points in time where we actually don't have a redundancy depending on the content. Okay, and here another proposition, primary keys. Now that is a great point because functional dependency, basically a key constraint is a special case of a functional dependency. Because a key essentially says that if we have this set of columns here, then it will uniquely determine the then it will determine the values in the other columns. So that is also a way of like one special case of a functional dependency. The key always means that if you fix values for the key columns, then you narrow it down to one single row in your data. And that is a special case of a functional dependency because here essentially fixing the values for the key columns immediately implies values for all the other columns in the same table. And so for key constraints, we cannot really have redundancy. Here there's some other. Okay, this is a very good point. So the amount of space that I'm saving, it would depend on like how many entries I have for each of the columns on the left-hand side of a function dependency. Yeah, so that is true. But essentially, it also depends on which data I insert at runtime. When I'm designing the schema before runtime, then I might not necessarily know like how many entries I have for each value combination. But it is true, in the end, how much space you waste, it would depend on the specific content of the database. Absolutely correct. And here, when designing a database schema, we would nevertheless try to avoid redundancy as much as possible up to a certain extent in order to essentially make certain guarantees independently of what people later insert into the database. But I agree with that point, yes. Okay, very good, yes. So keys, primary keys, those are acceptable functional dependencies. Also, I mean, of course, if you think about trivial functional dependencies, for instance, like the TA name and the number of hours together imply the TA name. So that is a trivial functional dependency because here the set of columns on the right-hand side is a subset of the set of columns on the left-hand side. So that is always true. And there's no way to avoid those functional dependencies from holding within the same table. So that is also okay. We will see, we will classify those functional dependencies into some that are okay and some that are not okay in more detail later when we discuss about normal forms. But I already wanted to show you a little bit that not all functional dependencies are the same, and we might be more willing to accept some to hold in the same table compared to others. Now, functional dependencies allow us to detect redundancy in some cases, and we can try to decompose tables accordingly. But first of all, we have to find them. So one common mistake is to try finding functional dependencies by looking at the current database state if there is already a first version. Now, the thing is that functional dependencies, they must be guaranteed to hold for all possible database states. Now, the data that you see at some point in time, it reflects the current state, but just because a functional dependency holds for the current data, it does not mean that it will hold after updating the data or after inserting more data or deleting some data. So you cannot really tell just from looking at the data. There's essentially two sources for getting functional dependencies that are valid. The first one is domain knowledge. If we design a database for the university and we know that the university has a policy that TAs get paid the same salary if they work the same number of hours, then I can integrate, I can translate this domain knowledge into a corresponding functional dependency for my schema. Also, after having some initial set of functional dependencies, I can use algorithms in order to infer more functional dependencies. So those are the two sources. There's like some seed functional dependencies derived from your domain knowledge, and then there's those automated processes which can derive more functional dependencies. How can we infer more functional dependencies? So this is what we mean by the notation on the left upper side of this slide. If you have a set of functional dependencies F1, then it might imply a set of functional dependencies F2, and we denote this as you see here. And what that means is essentially that any relation which satisfies the functional dependencies F1 must also satisfy the functional dependencies F2. There's a method to infer all possible functional dependencies. We can prove, even though we are not going to do that here, that with this method you find all functional dependencies, and all functional dependencies that you derive, they are actually implied by the seed functional dependencies. This method uses 3 axioms called Armstrong's axiom. And if you keep applying those 3 axioms, then eventually you will get all the functional dependencies that are implied by a certain set. Yes, first of all, reflexivity. I mean, that is that refers back to those trivial functional dependencies that I quickly mentioned. And here basically it just says that X implies Y. That's a valid functional dependency whenever Y is a subset of X. Example again from before, the TA name together with the hours implies the TA name. That's not very useful, but clearly satisfied a functional dependency. Then I have augmentation, and that essentially means that if X implies Y, then X and Z also implies Y and Z. For instance, we could say, now we know that the hours implies the salary from the previous example. So why not? We can also say that the hours and the TA name imply the TA name and the salary. Again, I mean, that doesn't seem very useful, but it is certainly true. And then we have transitivity, and that essentially means that if X implies Y and Y implies Z, then X will also imply Z. So if the TA name implies the number of hours, and if the number of hours implies the salary, then the TA name also implies the salary. Right, so those 3 relatively simple axioms actually allow you to infer all possible functional dependencies. The closure of a set of functional dependencies, those are exactly all the functional dependencies that you can infer, and this is what you would get when infinitely applying Armstrong's axioms. We also sometimes compare different sets of functional dependencies on the same database, and we say that one is a cover for the other one if essentially the set of functional dependencies that you can infer from them is essentially the same. So saying that one set of functional dependencies is a cover for another set of functional dependencies is essentially saying that both of those functional dependency sets are essentially equivalent because you can infer exactly the same set of functional dependencies. The problem with those closures, with the set of functional dependencies that you can infer, is in practice they're extremely large. So it is quite impractical to deal with them. So we will see a method to narrow down the set of functional dependencies that we are interested in at any point in time a little bit later. Now, first of all, let's make a little example where we infer more functional dependencies from an initial set of functional dependencies. So here we have a set of 3 functional dependencies given. This is a set F. We know that the course implies the lecturer. The course implies the department, and the lecturer together with the department implies the office. Maybe the lecturer alone isn't yet sufficient because people could have the same name in different departments, but a lecturer and department, that should imply the office. Now, a couple of things that we can, for instance, infer here. For instance, we have the constraint course implies a department. Via augmentation, we can just add the same attributes to both sides of that functional dependency. If we add department on both sides, then we would get course and department implies department. Now, those 2 sides of the functional dependency, they have set semantics. So here, if I add department to the set which already contains department, it will just remain department. Now, then we have course and a lecturer implies department and lecturer. So here we have essentially added a lecturer to both sides of the second functional dependency in F. And we have course implies office. Now, this one might be a little bit harder to see. So we're going to go a little bit more into detail there, how we can infer this one based on Armstrong's axioms. So here we have given those 3 functional dependencies marked up in blue, and now we infer the ones given in green. And at the very end, you see we infer the functional dependency that we are interested in, which was the one course implies office. So we will see how we can get there in multiple steps. So here we have a course implies a lecturer on the, like that is the given one, number 1. And now we add course on both sides, which doesn't change anything on the left-hand side, but to the right-hand side, it adds course. So that is the augmentation axiom. Number 5. So now we have course implies course lecture. Okay. All right. So for number 5, we can use a number 2, which is course implies department. And here again, we can use augmentation and add lecturer to both sides of the functional dependencies. Then we get number 5, which is course and lecturer together imply lecturer and department. And now if you consider number 4 and number 5, then we can apply transitivity, because in 4, course implies course and lecturer, and course and lecturer implies lecture and department based on 5. So also course implies directly lecture and department via transitivity. And now we get a 6, and if you combine 6 with a 3 and apply transitivity again, then we also get the one that we were looking for, which is course implies office. So this is how one example how we can infer new functional dependencies using Armstrong's axioms. Any questions on this? All right. Now, we are at the end of our time slot. I already mentioned that functional dependency closures can be extremely large, so they're impractical to handle in practice. This is why next time we will start by introducing attribute closures, which narrow down the functional dependencies that we are trying to infer. In general, next time we will discuss in more detail about how we can exploit those functional dependencies in order to come to better database schemata with less redundancy. Have a nice day, and then I see you again on Wednesday.